All right, I've been working inside of Visual Studio Code here to work with my notebook files this week, basically because I installed a new version of Anaconda and Jupyter Notebook, and it was kind of choking on me when I was scrolling, and I got frustrated and said, I'm not doing it. I don't have time for this, and switched over to Visual Studio Code, which I feel is a little bit more stable. I did in my little folder here. If you're using Visual Studio Code, I attach to my folder that holds all my machine learning code. And I have the two dependency files that are provided for this week. One is the starter notebook file, and then the iris flower data. This is a very classical data set, by the way. I think we've talked about it before. And so those are the two files, these first two, that are in the dependencies that you need, that I provide in a zip format. What I do when I work on these exercises, I don't want to destroy the original file. So what I do right off the bat, and I usually do this in my regular file system, is I make a copy of the file that I'm starting with, and then I call it starter or original or something like that. Then I open that one up, start to do my code. So I'm going to do that. I'm going to open up this file, and it's going to load up. And then right off the bat, I'm going to go up to the file menu. I know this seems like why are you doing that? That seems like ridiculous. I'm going to save as again. So I'm making a third copy. And for right now, I'm going to call it working or in progress or something like that. And then when I finish, I'll make another copy that I call solution. Right. The thinking is I can always go back, and I'm not destroying the original work. Now, granted, you can download the dependencies again, so you're not really losing the starting point. But if you didn't have that, these are just like silly little strategies that coders do. And it's worked for me over the years. That's why I recommend it. All right, so this is in progress. Now, because the iris data set is really a very classic data set when you study data science for whatever reason, it's like every data science class I've ever taken, every program I've been part of, every seminar I've gone to where they talk about data, this is one of the ones they always use, right? And this is a data set. They tell you where it comes from. So this guy wrote a paper back in the 30s where he took irises and measured them in a few different ways. So the things that he measured were the sepal and the petal and their length and width and whatever. And he came up with all these data points about irises that are still used to this day, and whatever. It's interesting information, I guess. What you will notice, though, that because this is a notebook file, and this is what's cool about these notebook files, is it can include information, right? So there's just regular text in here. You can drop images in to show stuff, right? And then you'll notice that he took basically these data points for each type of iris, the length and width of the sepal, inches or in centimeters, and the petal length and width in centimeters, right? And identifying that there's those unique pieces of information. When we get in here, we have some of the standard libraries to load up, right? And pandas, numpy, matplotlib, seaborn, and scikit-learn. Those are all pretty standard for us right now, including very specific sublibraries and all the aliasing that goes on. Right? We've talked about all these concepts. We import the data set, right? Load it into, read the CSV file, load it into a data frame. And then we start to look at some of the data and how it's basically structured. Now, one of the things that's kind of interesting is this command here. This info command looks at objects inside of Python and then gives you a data dump as to what it is, how it's structured, what kind of data it has, and a bunch of other information, right? And this is kind of weird stuff because basically when you use the Python language, everything is an object, right? And those objects, when you learn about classes and objects in programming, there's a blueprint that you follow, and then there's the object that's created, and the object has its own attributes and parameters and data fields and methods and all that kind of stuff. And what this is basically telling us is what that information looks like. So what are the data fields? Well, we have length and width of sepal, length and width of petal, and the species, the data types that are included, how many are not null, what the data type of each field is, etc. Right? And then a sample of the data. What does the data look like? Now, of course, you guys hear me say this all the time. Whenever you have a data file, you should open it up and just look. What's in there? What does it look like? Right. And I mean, when you look at raw information like this, it really does not mean a lot to you. Right. But it does mean something to people that are studying irises that are, where it counts. So they start to look at, a bunch of different data points here. So in this case, they're doing a frequency distribution of the species, and they're doing a count. So what species are we looking at? Well, they have 3 different species, and we're looking at 50 of each. That's a pretty equivalent data set to look at the petal widths, the sepal widths and lengths and whatever, to compare them. Right? So now we have basically the 3 species are identified, and then we're going to basically add, information relative to it, right? So like for each one of these, we are going to run visualization, and what this is doing is it's showing that based on the species, and see how the species are colored, that the petal length for those tend to be in the same ranges. And so in other words, just by looking at the petal length, I can tell you what species it is. Isn't that interesting? All right. Same with petal width. This one maybe isn't quite so clear because the data is kind of chunky. And then there's the sepal length. Those tend to overlap a little more. The next part of the process is to choose the number of clusters, right? And notice that this is a repeating thing. So like we'll get to the point where we're going to iterate. So we're going to repeat steps 3 and 4. So we choose the number of clusters, select random points from the data as centroids, right? And then the data works it out. Assign all points to the closest cluster, recompute the centroids, and you just assign to the closest cluster, recompute. You just keep repeating those however many times you tell it to repeat. So the general form of this is, all right, for I in range 1 to 11, this is a loop, right? They're going to keep running this. So they're running it as a loop. And I think this is kind of an interesting approach, right? So the number of clusters is determined, right? So every time I go through the loop, it's going to start counting at 1, and it's going to iterate 10 times, right? If you guys remember your Python loops, it'll never reach 11. It'll get up to 10 and never reach it. So this will run over and over again first with 1 cluster. I want you to conceptualize this, then with 2, then with 3, so it's going to keep going like that, right? Until it reaches 10. The iterations stay the same, and none of the other things are adjusted. So, all right. Then we start to plot the results, and depending on the number of clusters, and then what this says is this is an acronym here, within cluster sum of squares, and the more iterations, the less distance, so the better the cluster is. So what this is showing us is once we get past a certain point, how clustered the data is. So if we only run it a couple of times, not quite so clustered. 4 times, a little better. But it's like once you get up to 8 or more, those centroids aren't really going to move. That's what this chart is telling you. All right. You can start to adjust this. So like if you want to just do this straight up and just force a number of clusters, like let's say 3, right? I'm not really changing any of the other stuff here. and we start to conglomerate the data. Notice like it shows us where the centroids are. Kind of an interesting data set, right? The yellow one makes sense. I guess the purple one kind of does, but a lot of the green and the purple data really kind of pollute each other. But I want you to keep in mind that this data set has already labeled the species. So the greens are greens and the purples are purples. Now, if it didn't have that, right, would it have the same overlapping data? I think that's kind of an interesting question. So one of the things that you will do in your homework, and we're going to wrap up here, and I know I'm already over time, as you look at unit 7, is basically you're going to adjust the n numbers and rerun these things, and what are the output differences. So the one that we were just looking at has an n of 3. What are you going to change to run it differently? Well, yeah, you're going to change that to whatever numbers I said for 5 and 9. You're going to run all of those. Very easy change, right? So I'm showing you how easy this homework is. So don't stress on it. And then you'll get different outputs as you do it. So you'll have to rerun this cell and rerun this cell. And then you'll get different outputs. And then you can also rerun the scatter plot. When you notice that as it switches to 3 dimensions, how different it is to read, for sure. There's also examples here for DBScan, but folks, we are over time, so I'll let you guys run through these. There's no homework attached to DBScan, right? So that's a part you're just going to play with. The part that's part of the homework is basically changing those n numbers and rerunning these and showing me the results. If you get stuck, please reach out for help. And that'll be it for tonight. So this video ends here.